I'd like to talk to you about Gills for buildings. This matters because of this graph. Buildings actually use more energy on this planet than many of the other sectors that we find ourselves more frequently in discussion about. And of that very large wedge of the pie we see up here, a substantial portion of it goes to heating, ventilating, and air conditioning buildings. So, heating, ventilating, and air conditioning buildings is a bit of a thermodynamic challenge. It's not the greatest challenge in the world, but it's a bit of one. We have to manage mixed gas streams. Sometimes we have to manage a separation of some of those elements out of the gas stream. We have to distribute and deliver this air to the places we want it, and we have to manage the temperature and moisture to within ranges that keep us comfortable and to which we've come to expect, although we don't always get it. But it also keeps us comfortable and healthy. So for a century or more, since we've had air conditioning, we've managed this barely with a fairly crude brute force system where we manage all of these variables with three simple elements: some fans, some heating coils, and some cooling coils. And it's just about been able to keep up and meet the demand for this air conditioning that we have so far. But the world is changing very, very rapidly. I don't need to say that to anybody in this room. But I would point out to you that these are not absolute magnitudes. These are rates of growth. And you don't have to think very hard before you realize, what is happening, quick recovery, to the demand for air conditioning around the world. And these primitive systems that we've been using to date are simply not going to be able to keep up. So there is one technology out there, one approach that we think could make a lot of difference, and this is adding a heat and moisture exchanger into this open loop system so that we reclaim some of the benefit that would be lost as it gets flushed out of the building in the waste stream and putting it back into the building. Now, we do this every single day in the regenerative braking systems of electric vehicles. We use these kind of recovery systems in many other technology areas today, and we do this in building ventilation systems almost never. And the reason is that the technologies, the products that are available to do this, quite simply don't pencil very often in the relatively low-tech and very, very low-cost world of building construction. So we puzzled on this and wondered if there was some better way to take advantage of this really great opportunity. And at first, we couldn't think of really any ways to improve on what was already out there until we started to look at fish gills. Now, fish gills are incredibly efficient exchangers in the biological world. They're, in fact, way better exchangers than some of the obvious choices that you might initially think of, like the lungs, of which each one of us in this room possesses a pair. But gills are actually much better exchangers, and here's why. There is 5 times the amount of oxygen in the atmosphere as there is in the water. So lungs get to do their job in an ambient of oxygen abundance, and gills have to do that same job in an ambient of oxygen scarcity. Here's another thing. A lot of these very complex multivariate biological problems that have been discussed at this conference are so complex that very often when you study them, you're not completely sure which variables in the system are being optimized against others. Not true with gills. Gills, the mathematics that describe gill architecture are absolutely constant and consistent throughout every single scale in the ichthyological world, and it's a very, very strong object lesson in how to design a hyper-efficient exchanger. So we took these lessons and we applied them like this. So what you see here is a representation of a building with a conventional, though smaller, air conditioning system in the background. I'll draw your attention to what's up front here. What you see is a very, very large polymeric membrane exchanger covering a very large surface area. We made it large so that that's how we get a much, much better advantage over conventional products. We can actually move the needle on the building energy use with this. And then we avoid paying the space premium penalty, which is what kills this kind of technology in conventional buildings. We avoid using all that space by leaving it large in 2 dimensions and squeezing it down in the 3rd dimension and making it into a part of the building wall. So here you have a very sophisticated exchanger operating right at the interface between interior and exterior, again, very much like a gill. So we took this idea and we prototyped it first with the ETH Zurich in Singapore for 14 months, and then here you see at Lawrence Berkeley National Laboratory, and we were able to clock a number of very, very attractive metrics here. So when you use this kind of a system, you get to save a lot of energy, it's true, but you also get to buy smaller, less conventional air conditioning systems, and you get to buy less wall system. So let's be clear, using different kinds of membrane exchangers like this in building ventilation systems is not new. What's new here is that we've changed the footprint to make this economically viable, to make it pencil. Last year, we won the award. We were named the #1 game-changing technology in the green building space. Right now, we're installing one of our early installations at Hartsfield-Jackson Atlanta Airport, and we think we have a solution to this very, very growing problem, and we think it really, really matters. My name is John Breshears. I'm the founder of Architectural Applications. If you know a project that you think could benefit from this, talk to me on the bus. Thank you very much.